In the autumn of 212 BC, the city of Syracuse fell to Rome after a 2-year siege. Roman soldiers poured through the streets. The general Marcellus had given explicit orders: find the old man, protect him, bring him unharmed. The old man was 75 years old, the greatest mathematician and engineer alive, and Marcellus wanted him more than he wanted any treasure in the city. A soldier found him in his courtyard, bent over geometric figures he had drawn in the sand. The soldier ordered him to come. Archimedes looked up briefly and said, "Nolli turber circulos meos, do not disturb my circles." The soldier killed him. Marcellus declared the killer a criminal. He arranged a funeral with honors. He transmitted the philosopher's property to his surviving relatives. And he wept, according to Plutarch, not at the fall of the greatest Greek city in the West, but at the death of one old man who had been thinking too hard to notice a war ending around him. That is the measure of Archimedes of Syracuse, a man whose mind was so completely elsewhere that the end of civilization, as he had known it, was less interesting than the problem in the sand. Syracuse, where Greek genius met Sicilian ambition. Archimedes was born around 287 BC in Syracuse, the most powerful Greek city in the western Mediterranean. A metropolis of perhaps 200,000 people, strategically positioned on the southeastern coast of Sicily at the crossroads of Carthaginian and Roman ambitions. His father Phidias was an astronomer, and the household was connected to the court of Hieron II, the tyrant who would later become Archimedes' patron, sponsor, and most persistent source of engineering problems. As a young man, Archimedes traveled to Alexandria, the intellectual capital of the Hellenistic world, home to the great library, the museum, and the concentration of mathematical talent that the patronage of the Ptolemaic kings had assembled from across the Greek-speaking world. There he studied with the followers of Euclid, formed a friendship with the astronomer Conon of Samos, and began a correspondence with the mathematician Eratosthenes, the man who would calculate the circumference of the earth with a stick and a knowledge of angles. Archimedes and Eratosthenes exchanged problems and solutions by letter for decades, a collaboration conducted across the distance between Syracuse and Alexandria that produced some of the most advanced mathematics of the ancient world. He returned to Syracuse and never left again. The city, the court, the problems Hieron kept presenting him, and his own inexhaustible mathematical curiosity were enough. The crown and the bath, what Eureka actually means. The story of Archimedes and the crown is the most famous scientific anecdote in history, and like most famous scientific anecdotes, it is probably simplified. The historical core is this: Hieron II commissioned a golden crown and suspected the goldsmith of substituting silver for some of the gold while keeping the difference in weight the same. He asked Archimedes to determine whether the crown was pure gold without damaging it. The problem was genuinely difficult. The crown had an irregular shape. Computing its volume mathematically was not straightforwardly possible. Archimedes knew the density of gold, the weight of a given volume, but could not measure the volume directly. He thought about this for some time, and then went to a public bath. When he lowered himself into the full tub and water spilled over the edge, the solution arrived complete. The volume of water displaced was exactly equal to the volume of the body displacing it. Any object, however irregular its shape, would displace its own volume of water. The crown's volume could be measured by immersion. Its volume compared to a gold bar of equal weight would reveal whether it contained a cheaper, less dense metal. He ran home through the streets of Syracuse, the ancient sources say without stopping to dress, shouting, "Eureka, I have found it." The experiment confirmed the goldsmith's fraud. The crown displaced more water than an equal weight of pure gold, proving it contained silver, which is less dense than gold and therefore takes up more space at the same mass. This observation became the foundation of his treatise on floating bodies, in which Archimedes formulated what we now call the Archimedes principle: a body immersed in fluid experiences an upward force equal to the weight of the fluid it displaces. It was the first systematic treatment of hydrostatics in history, and it remains the basis of naval architecture, submarine design, and the physics of buoyancy today. The lever and the ship. Levers had been used by humans for millennia before Archimedes. What he provided was the mathematical theory that explained precisely how they worked and allowed their power to be calculated in advance rather than discovered by trial and error. In his treatise on the equilibrium of plane figures, he proved that the force required to move a load is inversely proportional to the distance of that force from the fulcrum, double the length of one arm, and you have the effort required to lift a given weight. The principle led him to the claim that became one of the most quoted sentences in the history of science: "Give me a place to stand, and I will move the earth." He said this not as a boast but as a mathematical consequence. If a lever long enough could be constructed and a fulcrum found, the arithmetic was straightforward. The earth could, in principle, be moved by a single human being. Hieron asked for a demonstration on a more practical scale. Archimedes constructed a compound system of pulleys, a palimpsestos, connected by a single rope to a fully loaded royal galley that had been hauled onto the beach and that normally required the coordinated effort of many men to move. Archimedes sat on the shore, pulled the end of the rope with one hand at a steady pace, and the ship moved across the sand into the water. Hieron, watching, reportedly declared that from that day forward, Archimedes was to be believed in everything he said. Pi and the method of exhaustion. For Archimedes himself, the engineering was secondary. The machines were, as he reportedly called them, mere amusements of geometry. His true passion was mathematics, and his most significant mathematical achievement, the one he would have chosen to be remembered for, was not the hydrostatics or the lever theory but his work on areas, volumes, and the calculation of pi. The ratio of a circle's circumference to its diameter, the number we call pi, had been approximated for centuries before Archimedes, usually as 3 or slightly more. His contribution was to replace approximation with a method that could produce a value as precise as desired. He inscribed regular polygons inside a circle and circumscribed them outside, beginning with hexagons and progressively doubling the number of sides until he reached polygons of 96 sides. The true circumference of the circle was trapped between the perimeters of the inner and outer polygons, and as the number of sides increased, these two bounds converged. His result: pi lies between 3 and 10^71 and 3 and 1/7. In modern decimal notation, this gives a value accurate to 2 decimal places, a level of precision that would not be significantly improved in the Western world for more than 1,000 years. The method itself, trapping an unknown quantity between converging upper and lower bounds, is the conceptual ancestor of integral calculus, which would not be formally developed until Newton and Leibniz in the 17th century. He applied the same approach to the volumes and surface areas of spheres and cylinders, proving that a sphere inscribed in a cylinder has a volume equal to 2/3 of the cylinder and a surface area equal to the cylinder's lateral surface. He was so proud of this result that he requested it be commemorated on his tombstone, a sphere inside a cylinder, with no other inscription. When Cicero found a neglected grave in 75 BC, nearly 140 years after Archimedes' death, he recognized it by exactly this monument, overgrown with thorns near the Acradina gate of Syracuse, the figure still visible on the stone. Counting the sand, a number system for the universe. One of Archimedes' most unusual works is the Sand Reckoner, a treatise addressed to Hieron's son Gelon, in which Archimedes sets himself the task of calculating how many grains of sand would be required to fill the entire universe. The universe in question is the largest one he could imagine, the heliocentric model proposed by Aristarchus of Samos, in which the Earth orbits the Sun and the stars are at a vast and unspecified distance. The work has 2 levels. On the surface, it is an exercise in large numbers. Archimedes develops a system for expressing numbers of arbitrary size using powers of what he calls a myriad of myriads, 10,000 times 10,000, or 100 million, as a base unit. He then systematically works through estimates of the Earth's diameter, the distance to the Sun, the distance to the stars, and the size of a grain of sand, and arrives at the conclusion that the number of grains required to fill Aristarchus's universe is approximately 10 to the power of 63. On a deeper level, the work is a demonstration that the universe is finite and knowable, that no quantity, however enormous, is beyond the reach of mathematics. The very act of attempting the calculation was a philosophical statement: the human mind, given adequate tools, can in principle encompass anything. There is no number too large to be named, no distance too vast to be estimated, no quantity that mathematics cannot in principle reach. This was not obvious in 250 BC. Archimedes made it obvious. The claw, the catapults, and the burning mirrors. When the Roman general Marcellus arrived before the walls of Syracuse in 214 BC with a force of 60 quinqueremes, large warships each carrying dozens of soldiers and artillery, he expected a short campaign. The city had defected from Rome to Carthage during the Second Punic War, and Marcellus had the resources and the reputation to take it quickly. What he had not accounted for was the 73-year-old man directing its defenses. Archimedes had prepared the city over a period of years at Hieron's direction. He had designed catapults calibrated to different ranges, capable of being adjusted to fire at targets at varying distances from the walls, eliminating the dead ground where attackers could approach without being reached. When the Roman fleet attempted a night assault, hoping darkness would neutralize the defenders' advantage, Archimedes had arranged for stones and heavy beams to be dropped through holes in the walls onto the ships below. The most dramatic of his defensive machines was what later sources called the iron hand or claw of Archimedes, a crane-mounted grappling device that extended over the city walls, seized the prow of a Roman ship, lifted it partially out of the water, and then released it, dropping the vessel sideways or stern-first back into the sea, capsizing or shattering it. The mechanics of how this was achieved remain debated. The most plausible reconstruction involves a counterweight crane with a long arm and a rope and hook system, operated by a relatively small crew. Ancient sources describe Roman ships being lifted into the air, spun around, and dashed against the rocks. The burning mirrors are the most contested of his alleged weapons. Later authors, including Plutarch and Lucian, describe Archimedes focusing sunlight through a system of concave bronze mirrors, or polished shields arranged in parabolic formation, onto the sails and hulls of Roman ships, setting them ablaze at the distance of a bowshot. Modern experiments have produced mixed results. Focused sunlight can ignite dry wood under controlled conditions, but the practical difficulties of coordinating dozens of mirrors against moving ships at sea are considerable. The scientific consensus today is skeptical, though not dismissive. Whether or not the burning mirrors existed as described, the catapults and the claw were real, and their effect was decisive. Polybius, the most reliable ancient military historian, records that the Roman soldiers became so terrified of Archimedes' machines that whenever they saw a rope or piece of timber appear above the city wall, they turned and fled, shouting that Archimedes was unleashing his devices upon them. Marcellus, finding direct assault impossible, converted the campaign into a blockade. The city held for nearly 2 years. When it finally fell, it was not to any failure of Archimedes' engineering but to a betrayal from within during a religious festival, when the guards' attention had wandered. The Palimpsest, a book that came back from oblivion. In 1906, a Danish scholar named Johann Ludwig Heiberg traveling through Constantinople examined a medieval prayer book and noticed something unusual about its parchment pages. The text of the prayers was written over an older text that had been partially erased, the parchment scraped and reused, as was common in the medieval period when writing materials were expensive. Heiberg could make out fragments of mathematical diagrams beneath the prayers. What he had found was the Archimedes Palimpsest, a 10th-century Byzantine copy of several of Archimedes' works, later converted into a prayer book by scraping away the original text. The book disappeared after Heiberg examined it, resurfaced at a Christie's auction in 1998, and was purchased by an anonymous American collector who made it available for scientific study. Modern imaging technology, X-ray fluorescence, multispectral imaging, and synchrotron radiation, recovered the hidden text with a clarity Heiberg could not have imagined. Among the recovered works was the Method of Mechanical Theorems, a treatise in which Archimedes reveals, for the first time, the thinking behind his mathematical discoveries rather than just the polished proofs. And what the method reveals is extraordinary. Archimedes was working with concepts of infinitely small quantities, infinitesimals, nearly 2,000 years before Newton and Leibniz made them the foundation of calculus. He describes treating geometric figures as if they were composed of infinitely thin slices, balancing these slices against each other on an imaginary lever, and using the results to determine areas and volumes. The method is not, as he himself acknowledged, a rigorous proof by the standards of Greek mathematics. It was a tool for discovery, a way of finding answers that could then be verified by the method of exhaustion. But the underlying concept is unmistakably the integral calculus, developed intuitively by a man working in Syracuse in the 3rd century BC, and then lost for 2,000 years in the pages of a prayer book. The legacy, a mind the world borrowed from. Archimedes died in 212 BC. His works survived, imperfectly and incompletely, through Arabic translations made in the 9th century and Latin translations from those, reaching the scholars of medieval Europe and the Renaissance in a form that was missing large sections and contained numerous copying errors. And yet even in this degraded form, his influence on the development of Western science was direct and acknowledged. Leonardo da Vinci studied the Latin translations of Archimedes's mechanical works and filled his notebooks with diagrams derived from them. Galileo Galilei described himself as a student of Archimedes and explicitly modeled his approach to physics, the combination of mathematical theory and physical experiment, on what he understood Archimedes to have done. Isaac Newton and Gottfried Leibniz, developing calculus independently in the 17th century, were both working in a tradition that traced back through Cavalieri and Kepler to the method of exhaustion that Archimedes had used to calculate pi and the volumes of curved solids. The Archimedes screw, a helical surface inside a cylinder, rotated to lift water from a lower level to a higher one, is still in use today in irrigation systems, in grain elevators, and in modern sewage treatment plants. The principle of the lever underlies every machine that trades force for distance. The hydrostatic principle underlies every calculation of whether a ship will float. These are not historical curiosities. They are active components of the infrastructure of the modern world. What makes Archimedes unusual is not any single discovery but the combination. The range of what he covered, the depth to which he pursued each subject, and the quality of rigor he brought to work that was, in its time, operating at the absolute frontier of what human beings knew how to think. He had no predecessors adequate to the problems he was solving. He created the tools as he went. And when he was finished, he left problems that the best mathematical minds in the world would not fully resolve for 2,000 years. He asked not to be disturbed while he was thinking. History has been disturbing him ever since, and finding that the circles, once drawn, do not erase.